By the time 3I/Atlas reached its perihelion, astronomers detected the first clear evidence of non-gravitational acceleration acting on the object, a discovery that immediately raised attention across the astrophysical community. This finding was formally documented in a report prepared by Davide Farnokia, a highly respected navigation engineer at NASA's Jet Propulsion Laboratory in Pasadena. Farnokia, who earned his PhD in mathematics from the Galileo Galilei School of Graduate Studies at the University of Pisa in Italy, has established himself as one of the leading experts in the orbital analysis of small solar system bodies. His report outlined in precise numerical detail the unusual accelerations affecting 3I/Atlas as it passed within 1/36 astronomical units of the Sun, a distance corresponding to roughly 203 million kilometers. These accelerations contain two major components, both lying within the orbital plane of the object: a radial acceleration directed away from the Sun, and a transverse one perpendicular to the radial direction. The radial acceleration measured approximately 135 kilometers per day squared, which translates to about 9 times 10 per day squared, while the transverse acceleration was measured at 60 kilometers, or 4 times 10 per day squared. These values, though extremely small by terrestrial standards, are surprisingly large for an interstellar object with no visible signs of strong outgassing at the time of detection. If these accelerations are caused by the familiar rocket effect produced by volatile materials sublimating from the surface and generating jets of gas, then the physics of momentum conservation allows us to estimate the rate at which the object must be losing mass. Based on the measured acceleration, and assuming a typical thermal ejection speed of several hundred meters per second, it becomes clear that 3I/Atlas would lose roughly half of its total mass in a period of around 6 months. This is what researchers refer to as the evaporation half-life. Such a short half-life implies a dramatic evolution of the object over relatively short astronomical timescales. During the month that the object spends crossing a distance roughly equal to its perihelion separation from the Sun, it should lose approximately 10% of its entire mass. A mass loss of this magnitude would normally produce an extensive plume of gas and dust surrounding the object, something that should be observable with spacecraft and telescopes during the months immediately following perihelion. The European Space Agency's JUICE spacecraft, positioned in a favorable part of the solar system, is expected to be the first instrument capable of detecting this mass loss, likely in the first week of November 2025. Later, on December 19, 2025, when 3I/Atlas reaches its closest approach to Earth at a distance of 269 million kilometers, hundreds of ground-based observatories, as well as the Hubble and James Webb Space Telescopes, will have an excellent opportunity to observe it in detail. With this wealth of data, astronomers should be able to determine conclusively whether the object indeed lost about 1/10 of its mass due to sublimation of volatile ices as it heated up near perihelion. The possibility of strong evaporation also connects directly to the unusual brightening behavior observed in recent months. A new scientific paper, based on measurements from the STEREO, SOHO, and GOES-19 spacecraft during September and October 2025, reports that the brightness of 3I/Atlas increased steeply as it approached the Sun. The data indicates that its brightness scaled inversely with its distance from the Sun to the power of approximately -7.5, with an uncertainty of plus or -1. Such a steep dependency is extremely unusual for comets or other natural icy bodies. Typical comets brighten with distance following a much shallower power law, so a -7.5 slope suggests either extraordinary levels of activity or an entirely different physical process at work. If the object is undergoing rapid mass loss and producing a dense expanding cloud of dust and gas, this could plausibly account for the observed increase in reflectivity. But the rate inferred from the acceleration measurements still seems high even for a violently sublimating comet, and the fact that no massive dust coma was observed earlier only adds to the puzzle. Because of these discrepancies, researchers have also considered an alternative explanation for the non-gravitational acceleration: technological propulsion. If 3I/Atlas were equipped with some form of internal engine, whether chemical, ion-based, or powered by another advanced technology, it could naturally produce the measured accelerations without requiring massive evaporation. This idea becomes even more intriguing given another reported anomaly. The object appears to have become bluer than sunlight as it passed perihelion. For a natural object, this is extremely unexpected. Dust tends to scatter red light more efficiently, which usually makes comets appear slightly redder than the sun. Furthermore, the surface temperature of a comet at such distances is expected to be far lower than the 5,800 Kelvin surface temperature of the sun, suggesting that any thermal emission from the object should be redder, not bluer. Yet the reported color shift toward blue wavelengths introduces another puzzle. The ninth anomaly recorded for 3I/Atlas in the most recent compilation of its unusual properties. One possible natural explanation is the presence of ionized carbon monoxide, which can emit strongly in the blue part of the spectrum. But other interpretations remain open, including the possibility of artificially generated light or heat, especially if the object were being propelled by an engine. Even with the measured non-gravitational acceleration, the actual deviation from the expected gravitational trajectory would remain small. Over the course of a month, the displacement would amount to only about 10 times the radius of Earth. While this may seem large from a human perspective, it is negligible on the vast scale of planetary orbits and is insufficient to bring the object significantly closer to any planet than its original heliocentric trajectory would have predicted. This means that even if 3I/Atlas is undergoing unusual acceleration, it poses no hazard and its motion through the solar system will be only minimally altered. The broader scientific implications of these anomalies echo a well-known challenge in astrophysics. On the same day the report was discussed, another event highlighted a comparable issue. As director of Harvard's Institute for Theory and Computation, I regularly host a Thursday luncheon attended by more than 100 astrophysicists, where recent advances in the field are presented. During this session, one of the talks focused on the long-standing tension between the current measured expansion rate of the universe, the Hubble constant, and the value predicted based on observations of the cosmic microwave background, the relic radiation from the early universe. Despite numerous attempts over the years to resolve this discrepancy with new theoretical models or adjustments to observational techniques, the mismatch persists with strong statistical significance. At the end of the presentation, after the speaker demonstrated beyond reasonable doubt that the tension cannot be dismissed as a simple measurement error, I reminded the younger theorists present of an important lesson. It is poor scientific practice to assume that data must be wrong simply because it does not fit our existing theories. Instead, unexpected data should motivate deeper inquiry, greater creativity, and a willingness to question long-held assumptions. The same lesson applies directly to the case of 3I/Atlas. Whether anomalies are ultimately explained by exotic chemistry, unusual physical processes, or even technological activity, the correct scientific response is not to dismiss the observations, but to explore them with open curiosity and rigorous analysis. Interstellar objects provide rare and valuable opportunities to study material from beyond our solar system, and each anomaly they present may contain clues about planetary systems and civilizations elsewhere in the galaxy. As more telescopes and spacecraft collect data in the coming months, the nature of 3I/Atlas will gradually become clearer. But for now, its unexpected behavior serves as a powerful reminder that our universe still holds many mysteries, and that genuine scientific progress depends on our willingness to confront the unknown with humility and imagination.